Recommendations for electronic circuits prototyping. Use a 30-watt soldering iron to solder a component in Vero board. Use a soldering iron as sponge with water to clean the tip of the soldering iron. Use a good quality soldering wire to wire up your prototypes. Use a proper wire wrapping wire to wire up your prototypes. Use soldering fume extractor to protect yourself from the fumes of the soldering wire. Use a good quality tin-coated Vero board for your prototyping. In previous session, we have developed a program for fire angle control, and we have developed a program that if we'll press switch 1, the voltage across this lamp will be increased, and if we'll press switch 2, the voltage across this lamp will be decreased. Now we'll press switch 1 and we'll measure the voltage across this lamp. We have connected this voltmeter across the lamp. Now we'll measure the voltage across this lamp. Here we can check voltage across this lamp is 89 volts. If I'll press switch 1, the voltage will be increased further. Let's see. Here we can see the voltage across lamps are 163 volt. Now we'll decrease the voltages across this lamp by pressing switch 2. Here we can see now the voltages across this lamp is 0 volt. Now in this session we will develop a program to measure the temperature of the surface of this lamp. For this we will use a sensor which is called PT100. Here we have a temperature sensor, that is PT100 sensor, and we'll measure the surface temperature of this lamp using this PT100 sensor. PT100 is a RTD sensor, that is resistive temperature detector. The resistance of this sensor changes with respect to the temperature. First, we'll understand that what is a PT100 sensor and how can we convert the resistance of this sensor into voltages to make it compatible with this microcontroller. We'll develop a hardware circuit to interface this PT100 sensor with microcontroller here on this portion of the Vero board. So let's see what is a PT100 sensor and how can we interface the sensor with microcontroller. PT100 is a platinum resistance thermometer and it is a RTD, that is resistive temperature detector. PT stands for platinum and the number 100 gives us the resistance value at 0 degrees centigrade. PT100 sensor has the resistance of 100 ohm at 0 degrees centigrade, and at 500 degrees centigrade the resistance of PT100 is 280.90 ohm. Here we can see the conversion table of PT100 sensor, and we can check at 0 degrees centigrade the resistance of PT100 is 100 ohm, and at 500 degrees centigrade the resistance of the PT100 is 280.90 ohm. Here we can see the actual PT100, and here we can find the casing to protect this PT100 sensor from external damages. Here we can see the specific conversion range of resistance with respect to temperature from 12 degrees centigrade to 30 degrees centigrade. Now we'll measure the actual resistance of the PT100 sensor that we will interface in our circuit. Here we have the PT100 sensor that we will interface in our circuit. Now we'll measure the resistance of this PT100 sensor. Here we can check the resistance of this PT100 sensor is 109 ohm. Now we'll check the correspondence of this resistance with respect to temperature from the table of PT100 sensor. And here we can check from the conversion table that the resistance of 109 ohm falls between 23 and 24 degrees centigrade. So the temperature of the room is between 23 and 24 degrees centigrade. And here we can find a circuit to convert the change of resistance into voltages. We'll convert a temperature range that is from 0 to 500 degrees centigrade to the voltages that is 0 to 5 volt. And we know that the analog to digital converter circuit of microcontroller will convert these voltages that is from 0 to 5 volt into a digital number that is from 0 to 1023. Now we'll discuss the working principle of this PT100 amplifier circuit. And here we can check we are using two types of operation amplifier circuit. The first stage is non-inverting amplifier and the second stage is differential amplifier. Here we can see the conversion function of non-inverting amplifier, and here we have the output of differential amplifier. As we can see from the conversion table of PT100 sensor that the resistance of PT100 sensor, that is R, is directly proportional to the temperature, and to measure the temperature using PT100 sensor we'll convert the change in resistance to the change in voltage. So in this case we will develop a relation that is voltages will be directly proportional to the temperature, and we know that the temperature range is from 0 degrees centigrade to 500 degrees centigrade, and the voltage range will be 0 volt to 5 volt. We can write the relation between voltage and resistance using Ohm's law. So we can write V equals to I into R, And to have the relation that V is directly proportional to R, then I will be constant. To obtain this relation, that is V is directly proportional to R, we'll inject a constant current through PT100 sensor, and we can draw the circuit like this. A constant current source I, and we'll connect the PT100 sensor with this source. So the current will remain constant throughout the temperature range, that is from 0 degrees centigrade to 500 degrees centigrade. We can draw the circuit of non-inverting amplifier like this. Here we have the resistance R in, and here we have the resistance feedback, that is RF. Now we'll connect the power supply with operation amplifier, say 12 volts, and ground, and we'll apply the voltages at non-inverting input of this operation amplifier. So here we will write V in. Now we can write the output function for this non-inverting amplifier. So we can write V out equals to V in 1 plus RF over R in. Now we'll assign the value to the R in, that is 100 ohm. So we can write R in equals to 100 ohm. And here we can connect a variable resistor as feedback. And we'll select the value of feedback resistance, that is from 0 to 500 ohm. Now we can calculate the output voltages and the current through the feedback resistor using this range. And if we'll apply an input signal of 1 volt at the input of this non-inverting amplifier, and if we'll select the value of RF resistor as 0 ohm, then the output voltages will be 1 volt into 1 plus 0, because the value of RF resistor is 0. So we will have 1 volt at the output of this non-inverting amplifier. And in this case, we can calculate the current through the feedback circuit. As you know that the feedback resistance is 0 ohm, then the voltages at non-inverting input of this amplifier will be the same as the output voltage of this amplifier. So we can calculate the current, that is 1 volt divided by 100, that is 0.01, which is equals to 10 milliamperes. Now if we'll change the value of RF feedback resistor as 100 ohm, now we can calculate the output voltages for this feedback resistance value. So the output voltages in this case will be V out equals to 1 volt into 1 plus 100 over 100, which is equals to 1. So we'll have 2 volts at the output of this amplifier. And now we can check, here we have 2 volts and here we will have 1 volt. And in this case, the current through the feedback resistance will remain same, that is 10 milliampere. And if we'll change the value of feedback resistance, that is 500 ohm. Now we can calculate the output, and it will be V out equals to 1 volt into 1 plus 500 over 100, which is equals to 6 volts. Now we can check if the output voltages of this amplifier will be 6 volts and the value of feedback resistance is 500 ohm. Then again the voltages at inverting input of this amplifier will be 1 volt. So in this case we'll also have the constant current, that is 10 milliampere through feedback resistor. So here we have seen that for different values of feedback resistors, the current through the feedback resistor will remain same, that is 10 milliampere. And we'll connect the PT100 sensor as a feedback resistance in our circuit. As you know that at 0 degrees centigrade, the value of resistance of PT100 sensor is 100 ohm. and at 500 degrees centigrade the value of PT100 sensor is 281 ohm. Now we'll connect the PT100 sensor as feedback resistance of the non-inverting amplifier. Here we have connected PT100 sensor as feedback resistance of this non-inverting amplifier, and we'll set 1 volt here, and we can write the output function of this non-inverting amplifier as Vout equals to Vin 1 plus Rf over Rin, and we know that the value of Rf will change from 100 ohm to 281 ohm, and we have applied 1 volt as Vin. So we'll have the output voltages at the first stage of this PT100 amplifier, that is from 2 volts to 3.81 volts. As we know that the value of Rf will be 100 ohm at 0 degrees centigrade, and the value of Rf will be 281 ohm at 500 degrees centigrade. So we'll have the voltages that is from 2 volts to 3.81 volt at the output of this first stage of this PT100 amplifier. And here we can write the value of Vout for two conditions, that is for 100 ohm. So we can write Vout equals to 1 volt 1 plus 100 ohm divided by 100 ohm, and we have connected 100 ohm resistance at the input of this non-inverting amplifier. So we'll have 2 volts at the output of first stage, and now we can calculate the Vout voltages against 281 ohm resistance, that is 281 ohm, and we can write Vout equals to 1 volt into 1 plus 281 ohm divided by 100. So we'll have 3.81 volts. Now we'll subtract these 2 volts at the final stage of the PT100 amplifier coming from the first stage of this amplifier. So here we'll use a difference amplifier, and we'll draw the circuit of difference amplifier like this. And here we can see the standard circuit for difference amplifier, and we have connected 4 resistors in this amplifier configuration, and we know that in difference amplifier we have 2 Rins, that is Rin, and this resistor is also Rin, and here we have 2 feedback resistors, that is Rf and Rf, and we can assign the name to these 2 inputs, that is V1 and V2, and we can write the output function like this: Vout equals to V1 minus V2 multiplied by Rf over Rin. Now here at V2 we'll apply the reference of 2 volts to subtract these 2 volts coming from the first stage of this amplifier. So here we'll apply a 2 volt reference. and we'll connect the output of the first stage of the amplifier to the V1 input of the second stage of this PT100 amplifier. So we'll connect the output to the V1. Now we can calculate the output of this difference amplifier for two conditions, that is for 0 degree centigrade and for 500 degree centigrade. As the voltages at V1 at 0 degree centigrade will be 2 volts and at 500 degree centigrade the voltages will be 3.81 volt. At 0 degree centigrade the voltages at V1 will be 2 volts. So we can calculate the output voltages of this difference amplifier. So we can write Vout equals to 2 volts minus 2 volts which we have applied at V2 input minus 2 volts and RF over Rin. So we'll have the 0 volts at the output of this difference amplifier, but at 500 degree centigrade the voltages at V1 will be 3.81 volts. Now we can calculate the output of this difference amplifier for 500 degree centigrade. So we can write Vout equals to 3.81 volts minus 2 volts, and if the RF and Rin value will be same, then we'll have 1 here and we'll get 1.81 volt, but we require 5 volts at 500 degree centigrade. So we'll set the gain of this difference amplifier using RF and Rin value. Now we can calculate the value of RF if we'll select the value of Rin, and we'll select the value of Rin as 100K. Now we can calculate the value of RF. Now to get 5 volts at 500 degree centigrade, we can calculate the value of RF like this. Vout will be 5 volts equals to, and the difference is 1.81 volt multiplied by RF over 100K. Now the value of RF resistor will be RF equals to 276.243K. As 276.243K is not a standard resistor, so we'll use 270K resistor instead of 276.243K. And now we'll develop the hardware of this PT100 amplifier on Vero board, and we'll interface this PT100 sensor with microcontroller. As we have converted the temperature range, that is from 0 degree centigrade to 500 degree centigrade, into the voltages, that is from 0 volt to 5 volt.